All right, get this. We're diving into Euclid's Elements. And no, this isn't that geometry class you're remembering from high school. You sent over these, what are they, lecture excerpts, right? From a Korean series about Euclid. And I gotta say, I get the feeling you're interested in way more than just, like, what angles and triangles, am I right?
Absolutely, yeah, you hit the nail on the head. What makes these lectures so interesting is how they explore Euclid's ideas, from ancient Greece, and how they've had this impact across, well, centuries and cultures, an impact that goes way beyond just math.
It's pretty wild, right? I mean, these geometric principles, we're talking thousands of years old, and they're still relevant today. Everything from philosophy to, get this, even science fiction.
Exactly, and that just shows how powerful Euclid's work is. It's not just about, like, memorizing geometry. It's more like this framework for thinking logically, for building an argument, proving a point, and that, well, that goes beyond just one field.
So it's like what, the OG art of persuasion, like way before influencers were even a thing?
Exactly.
Yeah.
And you know who's a perfect example? Baruch Spinoza, 17th century philosopher. He actually modeled his book Ethics after Euclid's Elements.
Wait, hold on. Ethics, as in like moral philosophy ethics, what's that got to do with geometry?
Well, that's what makes Spinoza so fascinating. He actually called it ethics demonstrated in geometrical order. Can you believe that? He thought you could prove moral truths with the same rigor and certainty as you could with those geometric theorems.
So instead of just saying like, stealing is bad because, I don't know, it just feels wrong, he's using definitions, axioms, all that logical stuff, just like Euclid, to build like an ethical system.
Exactly. He starts with the very basics, defines good, evil, happiness, then he lays out these axioms, those self-evident truths. And from that, he builds his ethical ideas step by step, like a proof.
Wow, that's a whole different way of thinking out right and wrong. Almost like he's trying to like remove emotions, make ethics as, I don't know, as absolute as a math equation.
That's a great observation. Whether he actually did it, created this completely objective system, that's debatable. But just the fact that he tried shows how influential Euclid's structured thinking was.
It makes you wonder, if he thought like that about everything, did he ever lose an argument?
Maybe that's a deep dive for another time. But you know who else was a fan of Euclid? And this one might surprise you. Abraham Lincoln, the 16th president. He always had a copy of Euclid's Elements on him, studied it really seriously.
Lincoln, the guy taught himself law, became president. What did he find so, I don't know, captivating about Euclid?
Lincoln always said that Euclid is what gave him that sharp logic, that legal mind. There's actually a story about him, late at night, studying Euclid by candlelight. He said something like, you can never be a real lawyer if you don't know what demonstrate actually means. He knew you needed airtight arguments, and Euclid, well, he provided the blueprint.
That's amazing, These figures from different worlds, centuries apart, and they both found something valuable in Euclid. Speaks to how universal that logical approach is. But get this, these lectures, they don't just stay in the past. They connect Euclid to, get ready for it, science fiction. Specifically, that movie Contact, where they use prime numbers to talk to aliens.
Right. It's a cool example of how sci-fi gets inspired by real math. Now, just to be clear, a prime number, it's a number bigger than one that can only be divided by one in itself.
Okay, so like 2, 3, 5, 7, those are all prime. But why use those to talk to aliens? Seems kind of random.
Well, prime numbers, they have this universal quality. They don't depend on any language or culture. If you run into some alien intelligence, chances are they'll understand what a prime number is.
Like a cosmic secret code. And the filmmakers, they use that so cleverly to show how we might find common ground with a totally different intelligence. But getting back to Euclid, these lectures, they don't just sing his praises, do they? They also warn about blindly accepting things as truths.
That's a good point. One of the excerpts, it actually shows this flawed geometric proof. It tries to prove that all triangles are isosceles, which we know is, well, not true.
Okay, now I gotta know. How can you have a proof for something that's just wrong? Is this where my geometry nightmares come back to haunt me?
No. Don't worry about that. This isn't about digging up old math anxieties. This messed up proof, it's actually great for understanding, how important critical thinking is, even in math, which we think of as all logic and certainty.
So it's like a reminder, even in something as perfect as geometry can seem, we can't just take things at face value. We got to look for those hidden assumptions, test the conclusions.
Yes, exactly. This flawed proof, it takes these seemingly logical steps and ends up at this impossible conclusion.
Right.
It just shows that even the most convincing arguments, they can be built on shaky ground.
Okay, you got me. I'm hooked. Walk me through this flawed proof. How do they try to tell us all triangles are isosceles?
So it starts off simple enough with a triangle. Let's call it ABC. The proof, it tells us to draw a line right through angle B, cutting it perfectly in half. We do the same thing to angle C. And these two lines we drew, they're going to intersect somewhere inside the triangle. We'll call that point D.
Okay, I'm picturing it. Divided those angles. We got our point D inside. So far, so good, right? Where's the trick?
Here's where it gets sneaky. Now we draw a line from point D, and this line needs to be perpendicular to side BC. We'll call the spot where they meet E.
All right, got it. Line DE inside the triangle, perpendicular to side BC. Lay it on me. What's the catch?
Now they use some basic geometry stuff to show that triangle BED and triangle CED are congruent. Remember, that means they're the same size and shape. And they use that same logic to say that triangles ABD and ACD are also congruent. And from all these matching triangles, they start pulling out all sorts of conclusions about equal sides and angles.
I think I see where this is going, building this whole case based on these congruent triangles. But I have a feeling it can't be that easy. What's the catch?
You got it. It's subtle, though. The proof, it assumes that point D, the one where our angle lines met, it assumes that point is always inside the triangle. And because of that assumption, they say that line AD is part of both triangle ABD and ACD. Seems like no big deal, but it's a big mistake.
Wait, why is that such a big deal? It makes sense that point D would be inside the triangle, right?
It seems right, yeah. And that's how the proof gets you. But picture this. What if we drew a triangle where angle A was obtuse? Bigger than 90 degrees. If we cut angles B and C in half like we did before, those lines are going to meet outside the triangle.
Oh, okay, I see it now. So in some triangles, point D would be outside. And in those cases, line AD isn't a side of both those triangles anymore. That throws a wrench in the whole thing.
Got it. The problem is they base their argument on something that isn't always true. And that's why this messed up proof is so interesting. It reminds us that even if something looks perfect, even if each step seems logical, just one wrong assumption can throw the whole thing off.
It's a good reminder to always double check what we think is true, right? Especially when things seem a little too neat.
You said it. And speaking of double-checking what we think is true, that's exactly what those mathematicians working on non-Euclidean geometry did. They looked at Euclid's fifth postulate, the one about parallel lines, and asked, hold on, what if this isn't actually a universal truth?
Now, that is interesting. We talked about how Euclid's work has influenced, well, everyone for centuries. But challenging the very foundation of his geometry, that's radical.
It was a total game changer in math. Think about it. For centuries, Euclid's axioms were seen as untouchable, like the absolute truth about how space works. But these mathematicians, like Janos Bolyai, Nikolai Lobachevsky, Carl Friedrich Gauss, they dared to think differently.
So instead of just sticking to the rules of Euclidean geometry, they're like, what if we tweak this one little thing, this seemingly untouchable rule?
That's exactly it. They imagined different worlds, different ways of doing geometry, worlds where parallel lines could actually intersect, or where the angles in a triangle don't add up to 180 degrees.
It's like they're explorers, right? Mapping out these uncharted territories, places that Euclid himself never even dreamed of.
And the best part, it wasn't just theoretical. These new geometries, they ended up being really important, especially in physics. Like Einstein's theory of relativity, that uses a non-Euclidean framework to explain how space-time curves.
So by questioning just one of Euclid's truths, they didn't just change how we think about geometry, but they also paved the way for a whole new understanding of the universe itself. That's incredible.
It just goes to show sometimes the biggest discoveries come from questioning what we think we know, from going off the beaten path.
It's a good reminder that there's always more to learn, more to discover, and sometimes to do that, we have to let go of even our most basic assumptions.
Absolutely. But you know what? Let's switch gears a bit here. Let's talk about another fascinating part of Euclid's work, the golden ratio.
Oh yes, the golden ratio, that mathematical idea that pops up everywhere. From ancient buildings to the way things grow in nature, hit me with some more of that mathematical magic.
Get ready to have your mind blown, because this is where Euclid meets, well, beauty. The golden ratio, we usually use the Greek letter phi for it, is about 1.618. It appears when you divide a line into two parts. And get this, the longer part divided by the smaller part is equal to the whole length divided by the longer part.
Okay, that's a very specific ratio. What's so special about it?
What makes the golden ratio so fascinating is that it's connected to beauty, to aesthetics, and it shows up constantly in nature. We're talking about the arrangement of petals and flowers, the spiral of a nautilus shell, even the proportions of the human body. It's like a secret code for beauty and harmony.
So it's not just some abstract mathematical idea. This has real-world significance.
You bet. And one of the coolest examples is how the golden ratio connects to building a perfect pentagon, a five-sided shape. That was something Euclid explored in depth in the Elements.
Wait, hold on. So this ratio isn't just in nature, it's also crucial for constructing a perfect pentagon using only a compass and straight edge. That's wild. How did Euclid even figure that out?
Well, it all starts with those angles inside a regular pentagon. Each one is exactly 108 degrees.
Okay, 108 degrees. Got it. Now what? How do we get from there to the golden ratio?
Now, imagine you draw diagonals inside the pentagon. Lines connecting corners that aren't next to each other. What happens? You get a really cool pattern. Not only do you create smaller triangles, but you also create a smaller pentagon inside the big one.
Pentagons inside of pentagons. Okay, this is getting good.
By looking at these shapes and using something called trigonometry, Euclid proved that the ratio of a diagonal of the pentagon to one of its sides is, you guessed it, the golden ratio.
No way. So to draw a perfect pentagon with just a compass and straight edge, you'd have to be able to divide a line according to this golden ratio. Euclid really was a mathematical genius.
He was. And get this, his work with the pentagon and the golden ratio didn't stop there. He kept going, exploring all these cool properties of this special ratio, showing how it connected to other geometric shapes.
It's amazing how this one concept, this ratio, connects geometry, beauty, and even nature. It's no wonder people have been fascinated by the golden ratio for centuries.
I know, right? From the ancient Greeks to Renaissance artists and architects, the golden ratio has been seen as the symbol of beauty, harmony, even divine proportion. Some people think that buildings made with the golden ratio are just naturally more pleasing to look at.
Which might explain why we see it everywhere, from ancient places like the Parthenon to modern art and architecture.
Exactly. It shows you how powerful and long-lasting Euclid's work is, and it reminds us about the unexpected ways math affects our world.
My mind is blown. Now I'm going to look at pentagons, seashells, even buildings like the Parthenon totally differently.
It really is incredible. It's like Euclid's work still has the power to surprise us, connecting these things that seem totally different. And speaking of connections, these lectures also highlight this fascinating link between Euclidean geometry and the world of prime numbers.
Prime numbers. Now that feels like a bit of a jump. How can geometry be related to something as, I don't know, abstract as prime numbers?
That's a good question. And yeah, it might seem strange at first, but remember those prime numbers we talked about before? The ones that could help us talk to aliens in that movie Contact? Well, Euclid played a part in building the foundation for how we understand those numbers.
Okay, now I'm curious. We're talking about prime numbers, numbers bigger than one that can only be divided by one in themselves. What do triangles and circles have to do with that?
Good point. There aren't any prime number triangles or circles hiding in Euclid's Elements. It's more about the ideas he came up with. See, Euclid, while he was exploring geometry and numbers, he developed these key concepts like divisibility, greatest common divisors, and even the definition of a prime number itself. And those ideas, they might seem basic, but they became really important tools for mathematicians who came after him. Mathematicians who really dug into the mysteries of prime numbers.
So it's like he provided the tools, and those later mathematicians used them to build something even more incredible.
You got it. For example, one of the lecturers talks about the prime number theorem. It's a complex idea, but it basically tells you how prime numbers are spread out among all the other numbers. Now, Euclid didn't figure out the theorem himself, but his work, that laid the groundwork for it to be discovered.
It's amazing, isn't it, how all these mathematical ideas, even if they seem unrelated at first, are actually connected, like branches on a massive tree with Euclid's work as the strong trunk.
What a great way to put it. And that connection, that's what makes math so powerful. When we get these basic principles, we can start to understand the universe and its secrets in a whole new way.
Okay, before we move on, what other surprises do these lectures have in store? We've covered so much already, from old Greek philosophy to aliens in movies. What other rabbit holes are we going to jump into?
Well, hold on to your hats, because in our next part, we're going to dive into this really cool lecture that connects Euclid's work to how we understand the world. The very nature of knowledge and how our brains work. It's about how what we think is true might actually be shaped by our own perceptions, by how we're interpreting the world.
Now that is a thought-provoking teaser. Sounds like we're in for a wild ride, a journey into, reality itself. I can't wait to dig in.
All right, so we're back to our triangle, ABC. Remember that?
Yep, good old ABC. Just chilling like a regular triangle.
Now, this tricky proof, it tells us to draw a line straight through angle B, slicing it perfectly in half. Then we do the same thing to angle C, and guess what? These two lines we just drew, they're going to cross paths somewhere inside the triangle. We'll call that point D.
Okay, got it. Split those angles, got our point D inside. Everything still seem okay so far. Where does it get fishy?
This is where they get yeah.
Yeah.
Now we draw a line from point D straight down to side BC, making a perfect right angle. We'll call the spot where they meet E.
Gotcha. Line DE inside the triangle at a right angle to BC. Hit me with the curveball. What's the catch?
Now they get all official with their geometry rules, showing that triangle BD and triangle CED are, get this, congruent, same size, same shape. Then they use the same logic to say triangles ADD and ACD are congruent too. And from all these matching triangles, bam, they start making all these declarations about equal sides and angles.
I see where they're going with this, building this whole elaborate thing on these matching triangles. But I have a sneaking suspicion it's not that easy. Spill it. What's the catch?
You're way too sharp for this trick. They slipped in an assumption. See, they assume that point D, the one where our angle lines crossed, they assume it's always inside the triangle. And because of that teensy assumption, they say line AD is part of both triangle ABD and triangle ACD. No biggie, right, wrong, it's a big ol' mistake.
Wait, why is that such a big deal? It just makes sense that point D would be in the triangle, right?
That seems right. That's the thing. That's how they trick you. But picture this. We draw a triangle where angle A is obtuse. That means it's bigger than 90 degrees. Now, if we cut angles B and C in half like we did before, those lines, they're going to meet outside the triangle.
I see it now. So in some triangles, point D would actually be hanging out outside. And if that happens, line AD isn't a side of both those triangles anymore. That throws their whole plan out the window.
You nailed it. Their whole argument falls apart because it's built on something that isn't always true. And that's what makes this whole flawed proof so thought-provoking. It shows how even when something seems perfectly logical, one tiny false assumption can send the whole thing off the rails.
Okay, so always got to double check those assumptions, right? Especially when things look a little too perfect. But that reminds me of those mathematicians who were messing around with non-Euclidean geometry. They looked at Euclid's fifth postulate, that one about parallel lines, and were basically like, hold up, are we sure this is always true?
And that right there, that was a pivotal moment in math. Because for ages, Euclid's axioms were seen as untouchable, the absolute bedrock of geometry. But these mathematicians, folks like Janusz Bolyai, Nikolai Lobachevsky, and Carl Friedrich Gauss, they had the guts to imagine other possibilities.
So instead of just coloring inside the lines of Euclidean geometry, they were like, what if we shook things up a bit? What if we changed this one seemingly untouchable rule?
Exactly. They started imagining different ways geometry could work. Like, what if parallel lines could actually meet? Or what if those angles in a triangle didn't add up to 180 degrees after all? Mind-blowing stuff.
It's like those guys were explorers, charting out these uncharted mathematical territories, places Euclid himself never even imagined.
And get this, it wasn't just some theoretical exercise. These non-Euclidean geometries, they ended up having huge implications, particularly in physics. Einstein's theory of relativity, that bad boy relies on a non-Euclidean framework to explain how space-time bends. Wild, right?
So, hold on, just by questioning one of Euclid's truths, they didn't just rewrite the rules of geometry, but also helped us understand the universe in a whole new way. That's insane.
It just goes to show sometimes the most groundbreaking stuff comes from questioning what we think we already know, from venturing off the well-trodden path and seeing where it leads. And speaking of venturing off the path, these lectures take us on another detour, this time linking Euclid to something pretty cool. Prime numbers.
Prime numbers. Okay, now we're really switching gears. How can geometry have anything to do with something as, well, abstract as prime numbers?
It's a great question. It might seem like a stretch at first, but remember those prime numbers we talked about earlier? The ones that could help us talk to aliens in that movie Contact? Well, Euclid actually laid the groundwork for how we understand those fascinating numerical building blocks.
Okay, now you've piqued my curiosity. We're talking about prime numbers here. Those numbers bigger than 1 that can only be divided by 1 and themselves. Where do triangles and circles fit into all of this?
You're right to point out that there aren't exactly any prime number triangles or circles hanging out in Euclid's Elements. It's more about the foundational ideas he came up with. You see, as Euclid explored geometry and numbers, he developed some pretty important concepts. We're talking divisibility, greatest common divisors, and he even gave us the very definition of a prime number. These might seem like basic ideas now, but they became super important tools for later mathematicians who wanted to unlock the mysteries of those prime numbers.
So it's like he handed them the tools and those mathematicians used them to build something even more mind-blowing.
That's a great way to put it. Like one of the lectures talks about this thing called the prime number theorem. That's a pretty complex idea, but basically it explains how those prime numbers are sprinkled throughout all the other numbers. Now, Euclid didn't discover the theorem itself, but his work. That was the foundation for its eventual discovery. Pretty cool, huh?
It's wild how all these mathematical ideas, they might seem totally unrelated at first, but they're actually all connected. It's like they're all branches of this massive tree of knowledge, and Euclid's work is the sturdy trunk holding it all up.
What a fantastic analogy. And it's those connections that make math so powerful. By grasping these fundamental ideas, we can start to unravel some of the biggest mysteries of the universe.
Okay, so we've gone from ancient philosophers to aliens to prime numbers. What other surprises do these lectures have up their sleeve? What other rabbit holes are we diving into next?
Well, hold on tight because in our next segment, we're going deep into a lecture that connects Euclid's work to, get this, the very nature of reality itself. We're talking about how we perceive the world, how our brains make sense of things, and how all of that might be shaped by the frameworks we use to understand the world around us.
Ooh, that sends shivers down my spine.
That's deep.
Sounds like we're about to explore not just mathematics, but the very fabric of reality. I am so ready for this. All right, so we're back, and I gotta say, my brain is still trying to process all these crazy connections we've uncovered. Who knew that triangles and parallel lines could lead us to ancient Greek philosophers, sci-fi movies, and even the nature of reality itself?
It's amazing, isn't it? It really shows you the power of mathematical thinking, how it reaches into all these unexpected places. Euclid, he didn't just give us geometric proofs, he gave us a whole new way of looking at the world, even parts of it that seem totally unrelated to geometry.
Totally. But you mentioned earlier these lectures, they take us even further down this rabbit hole, right? Something about Euclid and knowledge and how we perceive the world. I'm ready to have my mind blown wide open.
Well, buckle up because this last lecture excerpt, it tackles a really big question. How much of what we know, what we believe as true, is actually shaped by our own perception, by the way we interpret the world?
Okay, that is a big question. Are we talking about like optical illusions here? Or is this something, I don't know, deeper?
It goes way deeper than tricking the eye. Remember that allegory of Plato's cave? This lecture, it suggests that in a way, even Euclidean geometry itself can be like a cave, a framework that, while helpful, can also box in our understanding of reality.
So by sticking so rigidly to Euclid's axioms, those things that seem like self-evident truths, are we kind of trapping ourselves?
Yeah.
Like those folks in the cave thinking that shadows are all there is.
That's the idea. For centuries, people thought Euclidean geometry, with its axioms about parallel lines, angles, and triangles, all that, was the only true geometry. But then, boom, non-Euclidean geometries came along and challenged that whole assumption.
And it's not just geometry, right? If we can be so wrong about something as fundamental as space, what other truths are we clinging to that might not be entirely accurate?
That's the crux of it. This lecture, it basically argues that we need to approach everything we think we know with a good dose of skepticism and humility. Whether it's science, politics, even our personal beliefs, what we hold as true today might just be one perspective, one model of reality that's limited by what we currently understand.
Wow, that's both humbling and kind of exciting, don't you think? Humbling because it means we don't have it all figured out, but exciting because it means there's always more to discover, more to understand if we're willing to question our assumptions and look beyond what's familiar.
You hit the nail on the head. And that might just be the most important takeaway from Euclid's Elements. It's not just about the geometry itself. It's about the power of critical thinking, constantly questioning what we believe, and always being open to new possibilities.
It's been quite a journey. We started with these Korean lectures about Euclid, and look where we ended up, talking about ancient philosophers, deciphering alien messages with prime numbers, even questioning the very nature of reality. Who knew math could be so mind-bending?
It's amazing what you can discover when you really dive into a subject, isn't it? It reminds us that knowledge is interconnected. Even fields that seem completely separate can shed light on each other. And most importantly, it shows us that there's always something new to learn, no matter how much we think we know.
Absolutely. And on that note, we'll leave you with this. What truths are you taking for granted in your own life? What assumptions might be shaping how you see the world? Challenge yourself to step outside those familiar frameworks, explore different perspectives, and never ever stop questioning. You never know what hidden truths you might uncover. Until next time, keep those brains buzzing and keep diving deep.